one thing before getting back to materials is there will be no class on Friday. This Friday, I have to be away, so what is that, the video? Oh, I know, you're just all like, oh. You can sleep in, great. Okay, I apologize and all that, but I don't think it's so important. Anyway, material. The second problem set is due on Wednesday. I had to back off on giving feedback because, so those of you who have taken it or worked on it and noticed that the feedback buttons, I think, is absent probably. I had it set up so you could get feedback before you'd finish the problem set, which was not so wonderful. There's no mechanism, as far as I can tell, in Colab to allow you to take it twice and then get feedback. So I have to turn the feedback on after the deadline is over. Software. Any questions about the homework stuff? I've got material to cover for it today, but otherwise, okay. Where I left off last time was actually with this question, which I'm not going to ask again. When a box or wagon slides to a stop, which of these two objects does work or negative work or no work on each other? And the strange thing that comes out is actually A was the right answer. I never sort of said it out loud. A is the right answer. The only obvious thing that's going on here is the box does negative work on, the table does negative work on the box. It slows the box to a stop, sucks the energy out of it. That energy seems to go nowhere because the box is unable to do work on the table. The table doesn't move. So where did the energy go? It got ground up into what's called thermal energy. So the energy is still there. It truly is a conserved quantity in nature. You can't get rid of it. But you can hide it in various ways. And one way to hide it is to grind it up into little teeny pieces and sprinkle it randomly among all the atoms and molecules that are the surfaces of those two objects, table and box. So it's still there. It's just in this kind of useless form. You can do this yourself, just rubbing your hands together. Surely you've done this sometime when it's cold outside and you're turning work into thermal energy, warming up your skin. A more extreme case of this, which always fun to try this one, is there's a wood peg in there and a bow to spin the peg. And some years this works, some years it doesn't. With any luck, the work that I do shoving this thing back and forth, pulling it toward me as it moves forward, pushing it away from me as it moves away from me, that work will become thermal energy in the peg and we'll get it to smoke, at least smoke. Yay! All right. Whew. So it started as useful work in principle. Again, I can do something other than starting fires. And it becomes thermal energy. And a question, so two things I want to make clear about it. One is that it's really ordinary energy. That is, the atoms and molecules that are now on those, that now have warmed up, they are bouncing against each other. And when they're moving, they carry with them the energy of motion, so-called kinetic energy. And when they are bumping into each other and bouncing off each other, they have potential energy in the forces between them. So this thermal energy is good old-fashioned kinetic energy and potential energy just chopped into little pieces. So that's one thing to make sure it's clear. You okay with that idea? It's not a new magic special energy. The other thing about it is it's not very useful. We will see that later in the semester that you can make use of thermal energy in certain circumstances, particularly if you've got two regions that have different temperatures. So if you've got a hot region and a cold region, they both have only thermal energy present. You can get some of that thermal energy and turn it into useful work and do things with it. And you do it when you let the heat flow from the hot thing to the cold thing. You can divert some of it and turn it into useful work. And that behavior of moving heat from hot to cold and stealing some and making work out of it is called a heat engine. And these ferocious storms that have been attacking the southern coast of the US are basically heat engines. They're using the flow of heat from hot to cold to do, maybe not such useful work, but to do work. You know, where did this tremendous energy come from? It came from the flow of heat from hot to cold. It started as all thermal energy. All right, to show you why it's hard to just simply turn thermal energy back into useful energy, just to illustrate it, it's really a story of, it's a statistical story. So I have a bunch of ordinary dice. You know, you craps anyone? I have a whole box full of these babies. I curbed my enthusiasm and only put out a few of them. But I should be able to look at this. Cam. Yes, you're looking down at the tops of the dice, and that's just how I just poured them in there, right? Well, you know, of course, that there ain't no way I'm ever going to get all one, I don't know what you call it. It's a lot of snake eyes, I guess. That didn't happen by chance. I deliberately organized that. So this is a very orderly arrangement of dice. In principle, it could happen by chance, but it would be so unlikely. I'd be here for years trying to get that to happen by accident. And to illustrate that further, if I take this lovely orderly arrangement, which you might consider to be like ordered work, the work that's all ordered in me shoving that bow forward as it moves forward. And if I allow disorder to get into the story, to let things get ground up into trouble, the reverse is extremely hard to do. It's easy to take something that's very orderly like this, and I'm not even gonna look. I think I can disorder it without looking. Whoops, it's not all ones anymore. So even without looking, I managed to pull that off. Now let me try to get it back to all ones without looking. One of these days, it'll come back to all ones and I'll just keel over. Obviously I didn't succeed, and you know from long experiences, it'll never happen. Not because the laws of motion forbid it, it's because the laws of statistics make it so unlikely that for all practical purposes, it never happens. And those are the same laws that do things like, they make it so when you take ordered energy and turn it into disordered energy, and you sprinkle it randomly among all the atoms and molecules, they cannot go undo that. They can't all organize their energy back together and make the bow move and do work on me. Woo, that would be a surprise. It doesn't happen, not because of the laws of motion. The universe allows it mechanically. It doesn't allow it statistically. It's like winning the lottery a whole bunch of times in a row. In principle, it's possible. In practice, it never happens. And the odds against thermal energy reorganizing itself into orderly energy to do something, to lift a ball up high after it's bounced all its energy into thermal energy, the odds against it are so incredibly huge because there are so many atoms and molecules that are each getting their share of this random distribution that they just will never get their act together to do things useful. Okay? So that's an introduction, I guess, to the story of thermal energy. We'll come back to thermal energy later in the semester where we'll see that, for example, thermal energy is associated with temperature, and there are interesting things that happen with thermal energy if you've got differences of temperature around. All right? Well, why bring up thermal energy? Let me go back to PC main. I usually forget to do that. Why bring up thermal energy? It's because one of the frictions creates the stuff. And remember, there are two kinds of friction, two main types of friction. There are other ones, but we'll set them aside, not worry about them. There's the friction of two objects that are trying to slide across one another, but have not started. That's static friction. And there's the friction between two surfaces that are actively sliding across each other. And it turns out only the sliding version turns work into thermal energy. Static friction does not. So if I've got, let me load up this little wagon with put something in it. So while it's not sliding, I'm pulling, but nothing's happening, I'm doing no work on the wagon is doing no work on the table's doing no work on the wagon, no energy's moving around, and no energy in particular is being wasted as thermal energy. Once I get this thing sliding, however, like this, now I'm pulling to the left, it's moving to the left. Let me stop the story, otherwise I'll just, anyway. While I'm pulling to the left, it's moving to the left, I'm doing work on it. And the table is pushing it to the right with sliding friction and taking the energy right back out. We're getting nowhere here, right? Initially, when I get it started, I did a little work on it and now has kinetic energy. But at this point now, it's moving steadily along. I continue to do work on it. If you don't believe me, do it yourself. I'm pulling, it's moving to the left in the direction of my pull, so I'm doing work on it. And the table is just sucking that energy out. It's pushing to the right. As the wagon moves to the left, it's doing negative work on the wagon. Where did the energy go? It didn't go into the table's motion or anything like that. It got ground up into thermal energy. The bottom of the wagon got warm, the top of the table got warm. Questions about that idea? That sliding friction, when two surfaces go across each other, takes some of the energy associated with the movement and turn it into thermal energy. Okay? That's why the smoke starts coming out of that peg. I have the peg moving relative to the fixed block of wood, and they're sliding across each other. They're turning my mechanical work, this useful form of energy, into thermal energy, which is not useful. All right. So this is the biggest problem with friction is, say in a vehicle, isn't that it causes two surfaces to grab onto each other. It's that it wastes energy. And again, wasting energy doesn't mean destroying the energy. It means turning the energy into a less useful form, thermal. And so a wagon, if you try to have a wagon that has no wheels and you try to go across the country in this, obviously you're going to end up with wasting a lot of energy. Also, that rubbing I told you last time wears things out. It actually damages the surfaces because they're sort of colliding with each other microscopically and taking off parts. And you've all seen the steps on ancient buildings that have, over the years, worn away. They're not flat and square anymore. They got kind of undulating surfaces where people's shoes have just worn them away. Similarly, your old pairs of shoes, where did the soles go and the heels? They didn't just like evaporate. No, they got worn away by sliding friction. And you've seen those effects all over the place. This is the burning rubber problem. If you spin the wheels of your car, you just literally wear off the rubber. All right. So what's a solution? A simple solution, which I'll come back to the more complicated solution. If you just put rollers underneath a surface, actually just two is enough initially, this allows for free movement without any sliding friction. So the energy is not wasted. And actually, there's still friction involved here. There's a reason why this wagon wants to go left, right, and not away from you or toward you. It's using the rollers, and there is grip between the rollers and the wagon and the rollers and the table. The grip of of static friction. Rollers don't slide across surfaces, they roll across surfaces. And that rolling motion, which I sort of think of as like touch and release, it lands and leaves. It doesn't scoot. It just lands and leaves. While the surfaces are in contact with one another, they can experience static frictional forces. As long as they don't actually slide in that contact point, they grip and they can do useful things like guide the vehicle. So static friction is not all bad in a car. You actually want it, otherwise you can't steer. You want the wheels to land on the pavement, to grip left, right, so that the car doesn't like randomly veer left or right. And it lands and leaves, and it gives you the ability to control which way the car goes. So static friction is great for a car. It's the sliding friction you want to skip. Wasteful. Okay? Fun and games then with energies. The forms of energy, just sort of like a summary, approximately. The three main categories, this is not like I would ever test you on this, like, name the three categories of energy. I mean, it's just naming things, which is not my favorite. I don't consider that science. That's butterfly collecting. But the three types, the energy that's associated with a moving object. So a basketball that's stationary has none of this stuff. Once it's moving, something that requires you to do work on it to have it happen, you have to push it as it moves in the direction you push. It suddenly is able to do things it couldn't do before. So when it's moving, it's got kinetic energy in its motion. The direction of its motion doesn't matter, just it's its speed that matters. The faster it's going, the more energy it carries. As I might manage to say before the end of this section, the energy that it carries in its as energy motion, it's not proportional to its speed. It's actually proportional to its speed squared. So if you double the speed with which something's moving, it carries not twice as much energy, but 4 times as much energy. This is a reason why high-speed collisions, for example, when you're driving a car at highway speed as opposed to local 30-mile-an-hour type speeds, you go 60 miles an hour versus 30 miles an hour. That doubling in speed means your car and you are carrying 4 times as much kinetic energy. And you don't want to have that kinetic energy do things like turn into thermal energy in you when you hit things. So speed is destructive because energy goes up so fast with increases in speed. You okay with that idea? That kinetic energy is proportional to speed squared? I could argue why it's true, but we'll leave it aside. So that's the energy in motion. Direction doesn't matter, as I said. And that's, in part, that's related to the fact that energy has no direction to it. It's just an amount. It's a scalar quantity. It doesn't have a direction. Later today, we'll come to two interesting quantities that do have direction. Potential energies. There are a whole lot of potential energies. Anytime energy is stored in the forces between or within an object, there's energy in that. That's potential energy. And so what I've got gravitational potential energy. You know, we've talked about this one. As I lift the ball upward and do work on it, I am investing into it energy, and the energy is in the form of gravitational potential energy. It's stored in the gravitational forces between the ball and the earth. And we assign all of it to the ball because the earth just doesn't care. All right, if I let go of it, it spontaneously turns that gravitational potential energy into kinetic energy. When it hits the floor and starts to dent the ball on the floor, the ball comes to a stop momentarily. It's a very brief instant, of course. It comes momentarily to a stop. It's very low. It's very stopped. No kinetic energy, no gravitational potential energy. Where'd the energy go? It's in the elastic deformation of the surfaces. They've bent. And they're like springs waiting to release that energy. So that's what I've got there is elastic potential energy. And this is my favorite little elastic potential energy. You probably had a can like this when you were a kid, right? Uncle Fred, you want some mixed nuts? Ah! It's a vicious snake. And you do work shoving it back in. I push it in as it moves in. So I'm packing energy into this can. And then you go to the same person and you see the same thing, right? Uncle Fred, yeah. All right, you see it. Okay, so elastic potential energy is all over the place in stretched springs, bent surfaces, snakes shoved into cans. Magnetic energy, I can get some magnets to jump at each other or fly apart. You've seen that kind of stuff too. Electrochemical batteries are nifty examples of energy that's stored in the form of chemicals that have higher energy, chemical potential energy, that they can release in doing things. I could light something on fire, and that would be one example of chemical potential energy becoming a different form of energy. This is my current favorite, which involves a small light fixture here. And ready, get set, go back. I just think this is cool because it's so much light. from such a dinky little package. I mean, woo! All right. I guess more fascinating to me than anybody else. All right. I'm easily amused. Nuclear, I'm going to skip. It's, yeah. Electric. So this, I'll go out with a bang here. These devices, they're called capacitors. Those of you who are in 1060 know these guys. They can store energy in the form of electrostatic potential energy, the energy between charges. There are within this effectively two surfaces very close to each other, and I'm going to pile positive charge on one surface and negative on the other surface. And that will store a lot of energy, separating charges like love to get together, opposite charges, opposites attract. So I am going to take all the positives, lots of positives, shove them on one surface, lots of negatives, shove them on the other, an action which will invest them with lots of potential energy. They would love to get back together, and I'll let them do that shortly thereafter. I can't pull them apart with my fingers. I need help. So I will use electrostatic potential energy, or electrochemical potential energy, just like with these batteries, to pull them apart. I'm going to use batteries to pull them apart. The batteries are very good at grabbing charges and pushing them against their will one way or the other. So the batteries are currently taking positive charges, shoving them on one surface, negative charges, shoving them on the other, and they're piling up. And it actually takes a little time. It's probably done by now. But it's not an instantaneous thing, because there really is a lot of movement in there. OK, so this is covered with positive charges. That's covered with negative. If I let them get together like this, ready, get set. Oh, that was pretty pitiful. I'm thinking dead batteries. There's a second set of batteries here if this happens twice. 2, 3, 4, 5, 6. OK, let's try. Second set of batteries. A problem is it sucks the energy out of these batteries really well. I saw a nice little spark that time. I'm happier with this set of batteries. Dancing and sound effects surely helps. At least helps me. All right, ready? OK. We can do better, but that, OK. One more shot at it. A couple of years ago, we did this and got it on a photograph of me doing it for somebody wanted to put it in some online, something or other. And I was trying to do it, keep my eyes open while it goes. You can't do it. I couldn't keep my eyes open. The blink reflex is so intense. OK, come on, guys. Ready? That was better. All right, yes. All right. So that was releasing electrostatic potential energy. So all the potential energies, lots of them, all associated with forces between and within things. The last type of energy category is thermal energy. And it's nothing new. It's these other same kind of energies, except chopped up into little pieces, so you can't do much with it. Like undoing that flash and burning flying stuff is extraordinarily hard, extraordinarily unlikely. To recharge the capacitor where all the sparks fly together, their energy reassembles the positive charge on one plate, the negative on the other. It's not going to happen. Statistically, it's hopeless. OK? So static friction does not create thermal energy out of ordered energy. Sliding friction does. And so sliding friction just chews up useful energy and makes less energy, or relatively useless energy. So let's avoid it. And, oh gosh, let's see. Yeah. This is not a great question. But it's basically the idea that if you take a wheel and you just pull the wheel forward, it's on a cart, you just pull the cart forward, why does the wheel start spinning? I'm not going to ask the question. I'm just going to just look at it. The wheel was not spinning, and if I shove the cart forward, the wheel begins to rotate. And what did that? What did that was static friction between the bottom of the wheel and the table. If If the wheel moved without any forces from the table, it would just move like this, right? No rotate. But that doesn't happen because once the wheel touches the table, they don't like to roll. They don't like to move. They don't like to move relative to one another. Friction shows up and says, hey, wait a second, the table's stationary, the bottom of the wheel should be stationary. And that's what happens. The table effectively stops the bottom of the wheel from moving and forces the wheel to roll such that the wheel lands and the contact point with the ground is motionless, and then it lifts. So as you're driving along, so the front wheels of your car, not anymore, the back wheels of your car, those of you who have a car, are likely to be like this, undriven wheels. This excludes the all-wheel drive vehicles, but the vehicles that have only front-wheel drive have wheels in the rear that are not driven by a motor or engine. Instead, they turn only for one reason, because the ground they would skid on the ground if they didn't turn. So static friction between the ground and the wheel causes the wheels to begin to roll. Can you see how it's causing them to roll and why? Incidentally, when you're traveling down the road at whatever speed you like to go, NASCAR car goes zooming by at 180 miles an hour. The bottom surface of its wheel is landing on the pavement, motionless, and lifts off. The bottom of the wheel is always going 0 miles an hour. It's landing and leaving. You appreciate that? That's kind of bizarre. The top of the wheel, incidentally, is traveling twice as fast as the car. So if the car is going 180, the bottom surface of the wheel is motionless. The top surface of the wheel is going 360 miles an hour forward. Pretty fast. Okay, so static friction does show up in what's called a free wheel, a wheel that is not driven, that just simply moves with the vehicle, moves as the vehicle moves. Powered wheels, which is the other possibility, wheels that are spun not by the ground but by an engine or a motor. In that case, if they didn't touch the ground, the engine would simply turn them because it exerts a torque on them. That's its job. And when they then touch the ground, watch what happens to them. They grab the ground, and frictional forces appear between the wheel, bottom, and the top of the ground, static frictional forces, and they propel the vehicle forward. So the two kinds of wheels. A free wheel that is simply pulled forward by the vehicle and is turned by the ground, and the driven wheel that is turned by the engine and pushed forward by the ground. Is that okay? Any questions about that aspect of wheels, those aspects of wheels? I guess I have one more thing to show you with wheels. That is this. If you look at how the simplest of wheels, the old-fashioned wagon wheels, instead of just dragging the wagon across the ground, which would be really bad for the wagon and the ground and the oxen pulling it, you lift the wagon up on wheels, you shove a pin through the center of the wheel, an axle, and you allow the wheels to rotate in their touch and release manner with the ground, so that at the ground surface there's only static friction. The wheel is not skidding, it's landing and leaving. It gives some direction to the wagon and all that. Everything's great down here between the wagon and the wheel. The wheel and the ground. All right? There remains, however, a problem here at the axle. In this kind of arrangement where you've got a wheel with an axle going through it, this central donut, which is called the hub, rotates around the fixed axle, and they rub on each other. So in the old-fashioned covered wagon type stuff, there was friction, and worse, sliding friction between the hub, which is the donut, and the axle, which is the stick going through the donut. They rub on each other. It's okay with everybody? It's not a horrible problem because the distance traveled, there are big forces, frictional forces between those two. but the distance traveled is relatively small because everything's very tightly close to the center. There's not a lot of distance traveled. So the work done is modest, big force, but little distance. So that was the reason why things were not terrible. Nonetheless, the axle wears, the hub wears. You would put axle grease in there to try to keep the two from rubbing too much, but you basically lubricate them. But the ideal way to get rid of that sliding friction there is to insert little rollers between. Here are the rollers, just like I was doing with the box or the wagon. If you put rollers in a circle between the axle at the center and the hub on the outside, those little rollers will roll all day. They'll recirculate naturally, and there will never be any sliding friction present in that system. It's all touch and release on both surfaces. And that's the whole idea behind a roller or ball bearing. Let me show you a roller. I'll show you a ball bearing here. How do I get this document camera? That's a ball bearing. I've never held a fidget spinner in my hand, but I think they're full of ball bearings. Is that right? Right? So you can see these guys are balls. They're the balls sitting in there. Whether it's a roller like I got up on the table or whether it's a ball, it doesn't matter. But these two surfaces, the inner surface and the outer surface, or disc, or ring, can move very easily relative to one another. They're separated by these balls that roll. They never slide. They roll, and so there's only static friction in this. So in principle, you can get it going really fast, and that's the whole basis of the fidget spinners. And I've got gadgets in my lab, for example, that spin almost 100,000 times a second. A minute. 100,000 times a second is also possible, but that's getting crazy fast. And you couldn't do this if there were sliding friction around. You have to get rid of the sliding friction. How do you do that? You use bearings. And at extreme cases, the bearings can't be made of metal. They have to be made out of ceramics. It's extreme. But anyway, bearings, they make the world go round. Yeah, they're really important parts of all sorts of stuff. Your car's got bearings in it everywhere, keeping things from sliding across one another as they rotate. All right? Yeah, Sarah? In this one, this is a question about a freewheel, and it begins to roll because the ground pushes backward on the bottom of the wheel, trying to prevent the wheel from skidding forward. If it weren't for friction, the wheel would move forward. The wheel bottom would move forward as the ground stood still. Not good. So because the two grip each other, the ground prevents the bottom of the wheel from moving forward. It grips it. And so instead of skidding forward, it rolls forward. And that part that was originally touching lifts upward, heads backwards actually. It's facing backwards, opposite the vehicle's motion. Yeah. To look and see, watch the bottom's motion. It is not moving relative to the ground, and the consequence is that the wheel begins to rotate from your perspective away from you. Let me go faster. Ready? Woo! Okay. Wow. What made the wheel rotate like that? It must have experienced a torque, and it did. The ground pushed backward on the bottom of the wheel at a lever arm from the pivot. So the lever arm force rotates away from you. That's the right-hand rule. I mean, whether you remember that, I don't care. But that's the origin of that spinning motion, is the backward push on the bottom of the wheel. Is that okay? The reverse happens when you have a powered wheel. So that's what I just described is for a wheel that is free, that turns only because of the forward movement of the vehicle. If you have a wheel that's attached to a motor and engine that is being twisted deliberately, then without static friction with the ground, the wheel would begin to rotate faster and faster. But instead, it grips the ground. You notice that the bottom of the wheel is heading to the left. The table's stationary. The table will not like that. The table will say, bottom of the wheel, you must stop. And to do that, it pushes the bottom of the wheel to the right. And that push to the right is the only push on the wheel. And so the wheel accelerates to the right. So that's how a car works. It spins its powered wheels with an engine. The wheels would skid backwards. The wheel surface would head backward relative to the pavement. But the pavement doesn't like that. The pavement pushes forward on the bottom of the wheels to stop them from skidding. And that has two effects. It keeps them from skidding, and it also makes the whole car go forward. It's the only forward force, the only horizontal force in the car, forward. Okay? All right. That's my story of wheels and friction. And what I wanted to get to, so it was sitting on my mind here, is momentum and angular momentum, because they're part of the problem set. So I get boxed in by my own problem sets, for better or worse. So I've talked about energy at length, and sliding friction has this effect that it grinds up energy into uselessness. But energy is not the only conserved quantity. Yeah. Wow. Thank you. As I promised, I forget. Bumper cars. So energy is not the only conserved quantity in nature. There are very few, but they're all useful and important. So bumper cars is an example of exchanges of two other kinds of conserved quantities. It also involves transfers of energy, but I want to bring the other two kinds in. And hopefully many or most of you have had experience with bumper cars or something like bumper cars where things are smacking into each other. Billiards and pool count. I mean, it's all the same stuff. Things that bump into each other seem to transfer quantities that are related to motion in a way that energy has a lot to do with motion, but you can have energy that's not moving. This guy, when he was full of energy, nothing was moving. It was just all there in potential. There are other conserved quantities that are really associated with motion, and bumper cars bring them to light. So a first question to ask seems unrelated to bumper cars, but the merry-go-rounds, the little ones that show up on playgrounds or used to show up on playgrounds, they too have become very rare, like seesaws. But hopefully you had some chance to get on one of these little spinning discs with the things you can grab onto, and your friend gives it a push, and you go around in a circle, and you feel this tremendous pull away from the center, which is really just your inertia wanting you to go straight. So the question is this still familiar to you guys? You still do this stuff? Ever in your life? A couple times? Yeah. An app won't do it. It's hopeless. Pretty sad. Virtual reality, you just sit there your whole day, and the world goes by. Okay, so the question here is, if you're on the outside of one of these things as spinning fast, and you pull yourself to the center, which really requires pulling. It's hard work to get to the center of one of these things when it's spinning. What happens to the overall rate at which this thing spins? Does it speed up, slow down, or be unchanged? Okay with the question? How many think that it will spin faster? How many think it will spin slower? How about stay the same? Because the vast majority of you are going for spin faster. I'll show you spin faster. It is spin faster. So this is the world's littlest version of that spinning device. And instead of me climbing to the center, I'm going to pull the two of you. These are you guys. I'm going to pull you to the center. So here I go. I'm spinning, okay? And now I pull you to the center, and we go faster, right? So this is the skater trick, the ice skater. When they pull into a tight little spot, they spin like crazy. So the physics associated with that, it's a chronic problem. Ooh, stop moving. Yeah, the physics associated with that it's related to one of the conserved quantities of nature, known as angular momentum. So I'll come to that. We'll give it my best shot. So the answer to this question then is yes, it will spin faster. If you pull the mass, and therefore shrink the rotational mass of the object, pulling it in, it spins faster to compensate. Because what it is trying to do is maintain a constant amount of something. and that something is a conserved quantity known as angular momentum. So that's where that's heading. With bumper cars then, so the story of bumper cars is all things about moving cars tend to remain moving. You've seen that before, that's inertia, right? Well, now we'll look at sort of deeper under the hood of inertia. Associated with things tending to keep moving is that they're carrying with them a conserved quantity. That's very hard, that they cannot change without help. It's conserved. You can't destroy it or create or destroy it. It's fixed. So if you've got it, you have to have it. And it's associated with movement. So if you've got this quantity of movement, you're going to move. Getting it in and taking it out, taking that quantity in and out, takes some time. Involved in the transfer is time. Impacts, you can pass off this quantity of movement by hitting things. Then the time typically gets very small, but there are consequences to transfers that are rapid. The more massive the cars are in bumper cars, the harder it is to change their motion. So the less they respond to some other car giving them one of these quantities of motion. There's a quantity of motion associated with going somewhere, translation, and there's another one of these conserved quantities associated with rotating, spinning. And so there are two quantities of motion, one called momentum, I might as well name it. One's called momentum, that's the quantity that is associated with going somewhere. And the other conserved quantity of nature is angular momentum, which is associated with spinning. All right. So the questions I'll go through. The first one is this: does a bumper car carry a force? And the reason to say it in those terms is because it comes up in common language. That something was moving along through the air with tremendous force. Whoa! And then it hit. Things don't carry force. Forces are the influences that are exerted by one object or another. So if I go up to a wall and push on it, I can exert a force on it, it exerts a force on me. That's all very well. But when I'm heading toward the wall, I'm not carrying a force. Forces are between two objects. What's the other object? I haven't gotten to the wall yet. I am, however, carrying something with me. It's not the force. I'm carrying momentum with me. Momentum is this conserved quantity in nature, meaning that, again, if you've got it, you got it. You can't change it without giving it to something else. And you can carry momentum with you. It's when you hit things that you exert forces, and the forces are involved in transferring the momentum. So remember, energy is something you have, and work is the act of transferring energy. Same thing with momentum. Momentum is what you have, and there's a way of transferring momentum. It's given its own name. It's called an impulse. But let me show you show you momentum and hopefully two impulses. Right now I have no momentum. You can't hide momentum. There's no potential momentum. Momentum has an amount and direction. It's a vector quantity. And if you've got it, you'll be moving. If you've got it other than zero, you'll be moving. And it happens in the last line on that view graph it's actually the product of your mass times your velocity. I mean, people have no choice in that. This is what nature gives us. The more mass you have and the faster you're moving, the more momentum you carry in the direction of your velocity. So I'm going to get me some momentum. And I'm going to get it from something, because I can't make it. I need to obtain it from something else. So I'm going to obtain it from the wall. And what the wall is going to do is it's going to push me to the right for a period of time. How am I going to get the wall to do this? I'm going to push the wall to the left for that same period of time. So when I do this, there will be a full transaction of momentum between me and the wall. The wall will give me rightward momentum, and I will give the wall an equal amount of leftward momentum. Overall, the world's momentum won't change. It's just going to be redistributed. I'm going to have rightward momentum. The wall will have leftward momentum. It's got so much mass, the whole Earth, you'll never notice it. Ready? I'm going to get it. Here we go. The wall's going to give me rightward momentum. Whoa, we've got it. Now, I can't stop. I got to go. I got to give it to something. I gave it to the table. Ideally, I give it to the other wall, but my aim is not true. All right. The reason I have to keep going, you can say, oh, it's because of inertia. Yes, but the real secret under the hood of inertia is associated with momentum. And once I've got it, I can't get rid of it without giving it to something. If I'm lucky, I'll give it to the other wall. Here we go. I got it. I have to carry it with, I'm losing a little bit by way of friction to the ground, but mostly I'm carrying it with me, and now I'm going to give rightward momentum to the wall. And I did, and now I don't have any anymore. Can you follow the idea? It's really there. And you can't see momentum like, is it red or is it green? But you can see things carrying it. And in this case, just to show you, too many things I can possibly do. While I'm on that card, it's too hard. But let me get momentum out of the wall. Just show you a few details about momentum. I'm going to get some rightward momentum out of the wall, which will cost, the wall will lose rightward momentum, which is the same as obtaining leftward momentum. A negative amount of something to the right is a positive amount to the left. So I'm going to get rightward momentum out of the wall. It's going to be running a deficit of rightward momentum because I stole it. And having less than no rightward momentum is the same as having more than zero leftward momentum. So here we go. Now it's got leftward momentum. You can't see it because it's so massive. I've got the momentum to the right. I'm carrying it with me. I can't stop until I give it to something else. I give it to something else by pushing on it for a period of time. Force times time is how you transfer momentum. And the name for that is an impulse. And you can either, okay, so I gave an impulse to the wall. I gave all of my momentum away. I pushed the wall to the right for a period of time, and all my momentum is gone. Watch what happens if I keep pushing to the right. I end up with leftward momentum. What that means is, end of story. When I'm moving along to the right, I've got momentum, when I give it to the wall, if I give only part of it, I'll keep going. If I give all of it, I'll stop. If I give more than I had, which is possible, I will end up with a deficit of rightward momentum. This is what a deficit of rightward momentum looks like. It's leftward momentum. So you can have that happen. It happens all the time where an object gives something more momentum than it had in the direction it was traveling, and ends up going the other way. Example, this. I'm going to give the ball rightward momentum. It can't start moving right without me pushing on it and transferring rightward momentum to it. It came back at me. Where did that come from? It's because I gave it rightward momentum. It then gave the wall rightward momentum, and more than it had. So it ended up with a deficit of rightward momentum, which is leftward momentum. It came back at me. And then I took out its leftward momentum, and we're all back to where we started. All right? Yeah? Yes? Yeah, if you lose momentum to friction, which you were watching me do with that cart, I was giving it to the ground. It was being piddled away into the ground, little bits and pieces. Ideally, you carry it with you. And in bumper cars, you mostly carry it with you, and then you transfer it by way of hitting things and suddenly transferring large amounts. Give me 2 seconds to show you two things of import, maybe for the problem set. One is this, that you can transfer momentum as an impulse by it's force times time, right? Impulse, force times time. And as with work, remember work, you could do the same amount of work with a little force for a long distance or all that stuff. The same kind of gobbledygook happens for impulse. You can transfer all your momentum with a big force for a little time or a little force for a big time, and those often will matter. In bumper cars, it's a pretty strong force when they hit. So it's a pretty small, big-ish force, small time. If they took the rubber off and they had you steel against steel, it would be much faster, and it would involve much bigger forces, and you would swallow your gum, okay? So they deliberately put something soft around the bumper car so that you don't get creamed during these momentum transfers. Huge force, little time. These two balls differ from one another. This is a league ball, at least officially, supposedly a league ball, a hard ball. This is a softer ball. Everything about it's the same mass, same bounciness, all that. Difference is one of them has more give when its surface touches stuff than the other. And the consequence is that the softer ball transfers its momentum more gradually with time. Littler force, longer time. It's like an airbag for a baseball. This one, the league ball, you can pound nails in with this. And so this is a public service announcement. When your friends or children or something are playing baseball and are not very good yet, talented, yes, but they're starting out, don't play with one of these. It's a flying hammer. You can pound nails in it because it transfers all of its momentum so fast. This kind of ball, you can't pound. You can hit your hand with it. It's okay. Same momentum transfer, more time, less force. All right, I'll stop there. I've left one piece behind for the problem set on angular momentum, but can't do everything.